Hello and welcome to the fifth part of this GNU radio tutorial series. Here we're going to look at how to calculate the phase difference of a frequency of interest in an arbitrary input signal with respect to a known reference signal. Here our known reference signal is going to be the signal source. We've set it to be a sine wave of a particular frequency and fixed amplitude. Our input signal is going to be made up of the signal source, also a sine wave at the same frequency, but the amplitude can be varied at runtime using the slider. And eventually it will get through to this variable delay so that we can change the phase on a per sample basis using this other variable slider. In between we have this throttle block, the only one in the flow graph. The sample rate is set to 160 kilosamples per second, and this is 4 times our notional sample rate. You'll see that in other blocks we've set the sample rate to 40 kilosamples per second. All blocks within the flow graph will think that they're running at 40 kilosamples per second, but we're throttling at a higher rate so that things will actually flow quicker. They'll run faster, and therefore, for example, the GUI elements will update quicker as well. Now, we have a scope sync over here. If we follow the 2 input channels, you can see one goes back directly to the reference signal, and the second channel goes through, eventually arriving at the input signal of interest. The idea here is simply so that we can graph both sine waves on the same plot and therefore actually be able to see what they're doing. The objective is to find the phase difference between these 2 signals, between the 2 sine waves, and if we were operating with entitled constraints such that they were the same frequency and the same amplitude, you could do some arithmetic trickery to try and derive the phase. However, here we're operating with broader constraints, and the requirement should be that the input signal can be anything, and we just want to focus on one particular frequency of interest. And the obvious way to achieve this is by using a fast Fourier transform, and this is encapsulated in this block here. If we follow the data flow down from our reference source to get to the FFT, which requires a vector input, this is why the color is different. We've actually selected the input type to be float, and we set the transform width here using this variable. It's currently 1024. We're doing the forward transform, so we're going from the time domain into the frequency domain, and we're applying a window. This is optional, but you can use the window module and then the appropriate function to calculate the appropriate window by that name. So here we're doing Blackman-Harris with the same length as the transform width. So to get into this vector of floats that the FFT needs, at this high level we use the stream to vector block. And notionally what this does is it'll take this stream, this continuous stream of samples coming in, and instead of having single samples coming through, it'll combine them into a vector of length 1024, treat that as a unit and pass that through into the FFT block. At the lower level, this actually doesn't do much. What is important to note though is that the FFT will require a number of samples to be passed in that is a multiple of 1024, so that it can calculate for each iteration a complete proper transform which requires 1024 samples at a time. So once this actually calculates the forward transform, it's going to output a new vector, you can see this is a darker blue, of complex samples, also of length 1024. And it's important to realize that up till this point we've been dealing with samples in the time domain. After the Fourier transform, we're going to be dealing with output samples, complex samples in the frequency domain. And each of those complex samples is going to encode the amplitude and the phase of a particular component frequency in our input signal. So you can consider these as the bins of the Fourier transform coming sequentially out of the FFT. One complete FFT will obviously be contained within 1024 samples, and then it'll just keep repeating over and over after again. So this is a one-to-one transform in terms of the number of samples. Now, we want to focus in on one particular frequency of interest, and the way we're going to do that is firstly convert that notional vector type back into a continuous stream of complex samples. And we do that quite simply by using the vector to stream block with the same number of items. So outputting from here, we have the continuous complex sample stream of points from the Fourier transform, the bins, and we want to select the correct bin to then calculate the magnitude and phase of our frequency of interest. We do that by forwarding the sample stream to the skip head block. Now what this will do is it will skip the first 101 bins. And if we think about it, how do we derive that value? Well, we want to focus in on the bin that contains the frequency of interest. Now, we need to calculate the bin by looking at the frequency that we want to narrow in on, which is what we're generating here, as well as the transform width, which is 1024, and the sample rate that we're operating at. Now, I've done a bit of a trick here. I've actually tailored the frequency ahead of time so that it sits exactly in the 101st bin. Remember, it's 0 based because the 0 index bin is the DC component. So if we look at the variable f, which is the frequency that we're generating, we have this expression here. So we have the sample rate, which is 40,000 samples per second, divided by the width of the transform, 1024, and then we multiply that by the bin that we want to investigate. And this yields our frequency. So this has been tweaked ahead of time so that it works. But you could also use the similar sort of calculation if you're using an arbitrary frequency of interest to calculate which bin it will fall into. So we're going to skip the first 101 items, and this is important because we're actually going to skip the first occurrence of the bin that we want to investigate. This is because we forward the stream into keep one in n. So remember, the skip head will skip this certain number and then after that output all samples that come through the block. The keep one in n is a form of decimation where it will skip the first, in this case, 1023 samples, and then output the 1024th, then skip the next 1023, and so on. Because we've skipped the first occurrence of the bin of interest, we're then going to skip the remaining 1023, and that will take us up to the very next occurrence of that same bin in the second transform. So we skip all of the first transform, and then we continually, from the keep one in n block, output only that bin, only the sample that relates to that bin from every subsequent transform after that. And this is very convenient because from this moment on, we are only dealing with the complex sample that encodes the magnitude and the phase of the frequency of interest in both our reference and our arbitrary input signal. So we've been following the flow through from the reference signal. So our magnitude is going to be constant because we've set the amplitude to 1. I've got the complex to mag that would calculate the magnitude or the amplitude, and the complex to arg that will calculate the phase. It's also possible to use the complex to float block, but then I would have had to put a null sync on there to prevent errors. Here I can just disable the block. If we look at our input, arbitrary input source, that also flows through, and it goes into this virtual sync. The virtual sync is handy because it means that it will connect directly to whatever block is connected to the virtual source by the same stream ID. So we can actually follow the signal flow as if it was directly connected from the variable delay into this instance of the stream to vector block. You can see that's connected to the variable source here. We don't use this throttle, that's been disabled. So instead of having this web of connections, we can quite conveniently in the background thread the data flow through to this block here. If we follow it through, we have exactly the same blocks again, and if we follow it right to the very end, at this stage here we are looking at the same bin that represents the frequency of interest in both our reference signal and the input signal of interest. Since the input signal of interest can vary in amplitude, we also have this complex to mag so that we can keep an eye on the magnitude of the frequency. And then to find the phase difference between those two signals, we simply take the two angles output by the complex divided blocks and use the subtract block to find the difference. And then we put the resulting number on the GUI using a number sync. There's some more trickery going on down below, but before I get to that, let's just run the flow graph. Here we can see we have the two signals. Now, this is a quirk I found in GNU Radio. It might just be my particular setup because it's a little dated now, but these two sine waves should actually be on top of one another, so you should only see channel 1, the blue channel. For some reason in this particular flow graph configuration, by the time the samples arrive to the scope sync, it's been delayed, and even if I use the skip head, sometimes it works, sometimes it doesn't. So just bear in mind that in this particular case they should be on top of one another, and we just need to take this slight phase offset into account, and this is purely for the rendering of the sine waves. It doesn't affect any other part of the calculation process that I've outlined. If we look further up, we can see that the phase value is actually 0, so in terms of the calculation going on, there is no phase difference between the reference signal and the input signal of interest, and that makes sense because our delay value is set to 0, so it's not delaying or changing the phase of our arbitrary input signal. The amplitude is set to 1 as well, which is why they have the same amplitude on the scope. So if we start varying the amplitude now to begin with, you can see it changing on the scope there, and you can see the magnitude also changing. So the fast Fourier transform is extracting all the bins that make up the complete transform, and then we have our little filter using the skip head and keep one in N, extracting the only one bin of interest, and you can see that then being going through further calculations and then being shown here. The phase isn't changing except in those very final decimal places that we don't really have to worry about. Now let's set this back to amplitude 1, and let's start changing the phase. And this is where you should see the phase value change, and indeed it does. Remember that the phase is in radians, so I'm going to take it to approximately 180 based upon that little offset we had to take into account within the scope plot. You can see that it's approximately 180 degrees off where we started, and this almost matches what we have for the phase. So remember, since we're in radians, 180 degrees is pi. In this case it's almost negative pi. If we continue, then it wraps around and it starts decreasing from positive pi, 3.14, back down to 0, and then we almost have the overlap with that additional offset as compared to where we started, and then it continues in the same fashion if we keep going. So that appears to be working now. Fundamentally this is quite simple, but it's quite a powerful tool if you have particular operations or additional hardware that will induce sine waves onto some signal of interest. This trickery that's going on below, you can consider some hacks that you might employ in future just to help analyze your stream. Firstly, let's look at the output of this Fourier transform, which is operating on our arbitrary input signal. Remember that after the Fourier transform, we're not dealing with the time domain anymore, we're dealing with the frequency domain. So what happened if, for instance, you wanted to plot that somehow? Well, there are two ways of doing it. Both of these can be regarded as hacks, as I said. The first way is to actually take the output, put that through another fast Fourier transform, except in this case we're doing the reverse transform. So we're essentially undoing this FFT. If you consider this second FFT as your known process, then this will just be confirming that the first FFT worked correctly. Then we take the vector output, convert it back into a stream, and then once again put that into an FFT sync. So the idea is that we do an FFT, undo it, and then redo it again to confirm that the original signal is what we expect. And then the first FFT that we did is operating correctly because these two FFTs cancel each other out, and so essentially what you'll end up graphing, as long as these two final ones you know have been configured correctly, is the result of the first one. It's very convoluted, but it's hacky, and you'll see here that in fact it works. The frequency that we set was 3.9 approximately kilohertz, and if we look here on our FFT plot, you can see here that the first peak here in the positive side of the frequency domain is in fact at 3.9. We have a mirror here, it's symmetrical because remember we were operating originally on a floating point real stream, and when you do the FFT there you will get the mirror image in the top side, the top half of the spectrum. Usually you throw that away, which is why you need to divide the total frequency range by 2. So that's one way of doing it. The second way involves a little bit more trickery in the way that you deal with the vectors, and this can be quite handy, and hopefully this is just a bit of a thought exercise that you can apply to different scenarios. We go back to the first FFT again, and we take the output vector and we put it through this complex to mag block. So now what we want to look at is simply the FFT plot as we would normally do with an FFT sync, but instead we're going to actually do it with a scope sync. So what we do is we want to only look at the magnitudes of the bins, we ignore the phase information, and we could take the complex to mag, turn that into a normal stream that a scope sync will accept using the vector to stream, but there's no synchronization information. So remember, the scope sync just updates as samples come in, and then it would just have this odd FFT flick by, and you wouldn't be able to freeze it and have a reference as to where the 0 or DC bin exists. So what we're going to do is we're actually going to use the multiply const and add const in vector mode before we graph anything. So what we do is in the multiply const, we've got this funny expression here. Since we're operating in vector mode, the vector is of the same length as the FFT transform, we construct a constant which is simply has the first value as 0 and every subsequent value after that is 1, taking it to the same length as the transform. Now this actually wipes out the value in the DC bin, but that's not a concern. The other way of doing this properly would have just been to take the output directly into the next series of blocks, but this will serve our purpose here. The next operation after the multiply const is the add const. We do a similar thing. What we do is we now set the DC bin, or the index 0, to negative 1000, and we add nothing to the remaining bins. So what we've done is we forced the value in the first bin, the magnitude, to negative 1000, and we've left the rest of the bins untouched. And you can see here once again that we're constructing a vector of the same length as the transform width using this Python expression. So now after the add const we have vectors coming through the same length as of the transform, and we've set our own value into the first bin using these little expressions. We then take the log, because we're dealing with magnitudes. This is a nicer way of graphing by taking the logarithm, and then we put that into the vector to stream. That goes into our first input channel, and the second input channel is the original stream coming out of the add const that hasn't actually had the logarithm taken of it. So we're going to use the first input to actually view the FFT, and the second input to provide our synchronization using the bin that we manually set the value of. So now if you run it, let's look at the scope sync. We need to zoom out a little bit. So we know that we're going to have some energy in the bin that's related to the frequency of interest. What we need to do is synchronize it. So ordinarily you can see this would just be flying by, and there's no particular information we can glean from it. But if we go to the trigger mode and we switch to normal, switch to negative slope, and switch to channel 2, which is our synchronization information, you see that it's actually stopped. So what we now do is, because the first bin contains -1000, that's going to be where we start, and we're going to take the level below 0. So it'll synchronize on that -1000 bin. And if we take the time offset all the way to the left, to our notional time offset of 0, you can ignore the fact that it's labeled these in milliseconds. If we zoom in, then we can actually see, change the scale here, you can actually see what looks to be the frequency spectrum following a Fourier transform of our original signal. And here the original DC bin value is drawn off the screen so you can't see it, but the next repeating transform starts at the next green line, which goes all the way down to -1000, which is the channel 2. These peaks here will turn off channel 2 altogether. These peaks here are the same as the peaks here that were represented on our FFT and then reverse FFT concept, which is at approximately 3.9 kilohertz. And you can see, although you can't really get a sense of the frequency, you can actually just use this as a debugging technique to make sure that your transform is doing the correct thing. And once again, because we were operating on real samples to begin with, we have this symmetry about the middle frequency. So you could ignore and throw away the top half because it doesn't contain any more information. So you can see here that this is just a very simple, well, not quite simple, but convoluted manner of debugging the fast Fourier transform block itself. So you can see here that we have a peak where we expect, and everything appears to be working. If we change the amplitude now, we can actually see this updating, amplitude increasing and decreasing. And because we're only plotting the magnitude, we're ignoring phase. When I change the delay, although it's updating there, you can see down the bottom the bin of interest, the frequency of interest is not changing in magnitude. So that is actually working as it should. So although this has been a bit of trickery here, hopefully you can take this knowledge and apply it elsewhere to debug or do some other sort of signal processing. The final point before concluding is that once you've actually extracted the magnitude and the phase of your signals of interest, you could then, instead of just plotting them on a number sync, or you could also send them out on the network. And because we have 2 bits of information here, you can combine them into a single stream using the stream mux block. And this will create an interleave stream where the first sample in this instance is, if we follow the flow back, the phase difference, and the second in that interleave stream will be the magnitude of the frequency in our arbitrary input signal. Here the output then goes into the stream to vector. Because we have an interleave stream, we're going to take that notionally to the vector type of vector length 2, and then input that into a UDP sync, which is also set for vector length 2, and that ensures that it will always take in a multiple of 2, and this is also set to the floating input type, and then transmit that in a packet over the network to another computer that will receive this information. Finally though, another handy tool is GNU Plot, and we can use that by taking information from this flow graph and putting it into a file. So once again, we have the virtual source here with the stream ID delayed instead of having the connection run all the way up to here. We just use this source here. This is disabled. I won't actually run it now, but I'll just lead you through it. The FFT size, here we have actually set to our original FFT width, although if you wanted to look at the frequency components in a very, very fine amount of detail, so the resolution of your transform in terms of the frequency domain would be very high, you could actually use a very large number of bins, a very, very wide or long transform length, but just be wary that the greater you make this, the more memory it's going to use up. Here though, we've just stuck with 1024. That goes through the same process, stream to vector, FFT, complex to mag because we're simply interested in the magnitude components of each bin, and then we output that into a file sync. We've set the vector length here to the FFT size 1024, so that it will write groups of 1024 samples to the file. Now when we run it, this will start writing those samples to disk, and because we're doing the FFT transform, it'll just write the result of the transform over and over and over again. Now what we can do, this is storing it in the file as floating point values. You can use the raw to num_f program to convert that into text. So that'll put a new sample on each line and output it as text from this original binary file. So if you run that, it'll dump it out as a text file, and you can see if we look at that file, we have the values. The original column here is just the zero-based index. Then we can run it through a little Python program that I found helpful to do this sort of analysis. What it does is it takes in that text file, you specify the FFT width, in this case 1024, and it'll combine those into multiple series instead of having the single series. So if we run that, it's got the strides, and then it'll create 507 series from that. It'll ignore the residue at the end. And then what you can do is start GNU Plot, and then plot. In this instance, we've got 1, 2, 3, 4, 5, the first 5 series in that file, and we can see whether the correct bin has been selected so that we analyze the appropriate frequency in our input signal. Let's have a look, plot that. Once again, we have this symmetry, but if we zoom in on this peak that we see appearing here, then we can clearly see, even if we use the cursor and look at the tooltip, that this is bin 100, which is the 101st bin. Remember, we need to deal with zero-based indices since the first one is the DC component. And then we have this roll-off, which is due to the window that we used. If there was no window, then it would stay flat and the 100 value would immediately rise up. And you can see that this is the correct bin to be looking at for our frequency of interest. And that's how you can use GNU Plot. If we were to use a much larger transform size for this file dump, then that would, in the frequency domain, yield a much finer graph, and it would take far longer to load as well and render. But if you're, for instance, trying to calculate the baud rate of a signal using blind analysis, and the baud rate is very high, then you can use a very high transform width as well to narrow in on exactly the correct baud rate that you require, and I'll cover that in a later tutorial episode. So thanks for watching this one. Hope you've been able to learn a couple more new handy tricks, and see you in the next episode. Thanks for watching.